This is Lab 7, determining the unknown mass of a black hole. My name is Bridget Savitsky. The problem is that we have a star whose motion is obviously being influenced by a force at a certain location, but we are unable to see the source, and therefore it's hard to detect the mass. And so, the main result is that using the various principles of curving motion, gravitational force, Kepler's law, and the momentum principle, we're able to calculate the mass of the black hole. Looking at the model, we had to set some initial conditions, and this included the x and y velocity of the star. This was determined from the data of the positions of the star that was given. We needed the mass of the star, the position of the source of the force acting on the star, and a time step of 1 day in seconds, and this is a good unit to work with because we're working on an astronomical scale. And the certain parameters had to be adjusted to fit the data, and this included the arrow scale for all three of the vectors included in the model, and this was so that all the arrows would be visible, not so that one wouldn't be too large and one wouldn't be too small. The following steps were taken to ultimately produce the model. The time step was set, and all the initial conditions were taken into account, and we had to calculate the change in velocity and multiply that by the mass, get the change in momentum, then calculate the net force using the momentum principle by finding the change in momentum over time, and then calculating the parallel and perpendicular components of this net force. The model we're comparing the data to is the momentum principle, and there is no time where it can't be applicable to this data because it's a thoroughly tested model, and it is key to predicting how the vector errors are modeled on VPython. I'll go ahead and run the model. We can see what it looks like. So here we have three vectors. The blue arrow is the net force vector, the red is the perpendicular component of the net force, and the black is the parallel component. This is parallel to the tangential momentum, and this is perpendicular to the momentum vector. And it's important to note here that the blue net force arrow is not pointing towards the center of this ellipse. It is pointing towards the source of the force acting on the star, and this is an ellipse, and this goes along with Kepler's law. You note here that this VPython model doesn't necessarily show the way the star would exactly look with the exact speeds if we were to take, say, a video camera and record it, but it does show the accurate positions and force vectors that are acting on it. There are several concepts incorporated into this lab, including the gravitational force, and we used the magnitude here to determine the mass of the black hole. The momentum principle was also used because the star has a change in momentum over a certain amount of time, and that is equivalent to the net force that is acting upon the star. Because there's curving motion, we know that there's a perpendicular and a parallel component to the net force, and so we can calculate that separately, and also Kepler's law stating that the path of the object will be elliptical. We use this magnitude of the gravitational force, and we know that it's the same thing as the perpendicular component, the magnitude of that, and the VPython gives you the magnitude of the gravitational force and also the distance in between the star and the source of the force, and plugging in these numbers we're able to solve for m. And we get this number, 2.01 times 10 to the 31st kilograms, and this conceptually makes sense because a very large mass would be able to have such a strong influence on the star to affect its motion in that way. We know that the star is changing its momentum over a period of time, caused by a net force acting on it. And because we can see that it has curving motion, we know that something's making it change direction and something is making it change its speed. And what we can assume is because the gravitational force is the only force acting on it, this has a perpendicular component and a parallel component. And we know that the sum of the net force is the sum of its perpendicular component and its parallel component. And so therefore we can assume that its change in momentum over time that's making it change direction is the same as the net force in the perpendicular direction, and the change in momentum over time that is parallel to the tangential momentum vector is the same as the net force in the parallel direction. So what if a different black hole replaced the current one we were just looking at, and the star's motion is completely unchanged? Well, I think it's absolutely impossible to find the mass of the new black hole because there is the same position data. And if there's the same position data, all of our outputs that we got before are going to be the same. The velocity, the momentum, and the net force. And so the momentum principle accounts for these changes in stars' positions, but if they're the same as before, there's going to be no different mass shown.